Welcome back. In the last class we did a couple of more problems. So I wanted to do one more problem, which is a very nice problem because it gives you a flavor of what main theorem does and what really Galois theory does in terms of explaining how a given field extension behaves. So we do this one problem and then we move on to the next topic in Galois theory. So this is the problem number, so let me see, 9. Okay, so I want to do this problem in detail to understand what is going on. So let K over let's say F be a normal extension such that let's take characteristic 0. Okay, let K over Q be a normal extension such that the order of the Galois group is 8, and the Galois group has the property that sigma square is 1 for all sigma in the Galois group. Okay, so the question is, find all the intermediate fields of the extension. In fact, you can take Q to be F, but make it a characteristic 0 field, then this works. Okay, so the solution to this is the following. So first note that this is a Galois extension. Since characteristic Q is 0. So that means it's automatically separable. It is given to be normal, so it is Galois. So therefore, K colon A Q, which is the cardinality of the Galois group, because it's a Galois extension, and that's given to be 8. So you have a degree 8 extension. Okay, now let's use this very strong property of the Galois group. So let G be the Galois group. I'm going to write Galois group as G because it's convenient. Then sigma square is 1 for all sigma in G. This is the hypothesis given, right? This means, so order of, so basically orders of elements of gamma are basically sigma G are given like this. Order of sigma, so for sigma in G, order of sigma is 2 if is not identity, 1 of course if it is identity, right? Because identity also has this property, but it's also equal to identity, so it has order 1. But for every non-identity element, sigma is not equal to 1, sigma square is 1, so that is the order 2 element. That's an order 2 element. Note that also note G is abelian. This is because if sigma and tau are in G, let's say, then sigma tau inverse is tau inverse. Of course, sigma tau inverse is sigma tau, because square is identity, means an element is its own inverse. Sigma tau is equal to sigma tau inverse, but sigma tau inverse in general in any group, you take the product and take the inverse, you interchange the elements, right? So sigma tau inverse is tau inverse, sigma inverse, but tau inverse is tau, sigma inverse is sigma. So sigma tau is equal to tau sigma. So G is abelian. So G is an abelian group, order 8. Every element has order 2, every non-identity has order 2. So hence, so this is a group theory fact. Any abelian group which has this property must be isomorphic to Z mod 2Z cross Z mod 2Z cross Z mod 2Z. Okay, so this is a fact from group theory. Okay, so this you can, for example, prove using the fundamental theorem for finite abelian groups. You can write them as products of cyclic groups. In this case 8, so the only possibilities are z mod 8z or z mod 2z cross z mod 4z and so on. But in all of those cases, there will be elements whose order is not equal to 2, non-identity elements whose order is not equal to 2. So this is the only possibility. So with this data, now let's go about finding intermediate fields. So let L be a non-trivial intermediate field. So of course there are two obvious intermediate fields, K and Q, but we are interested in, right? So this is not 1, this is not 1. So L is not K, L is not Q. Those are there, those are already there, but what about others? So now there are two possibilities. Case 1, L colon, so we have two numbers whose product is 8 and they are both different from 1 because K is different from L, Q is different from L. So the possibilities are K colon L is 4 and the other possibility is case 2, K colon L is 2, right. So we have either 2, 4 or 2 here, similarly 2 or 4 here, because only divisors of 8 are 1, 2, 4, 8. We don't want 1 and 8 to appear here, so 4 and 2. 4, if this is 4, this is 2, this is, if this is 2, this is 4. So now let's analyze these. In this case, L is equal to K power H, where H is a subgroup of G of order 4, and in this case L is K power H, where H has order 2, right. This is all from the main theorem. So K colon L, this I will write one more time. If L equals, maybe I will start here, if L equals K power H, then K colon L, which is of course K colon K power H, is cardinality of H. This is not even main theorem, this is our theorems that, preparatory theorems that we proved before the main theorem. So K colon L is 4 means order of L H as 4 is 4. So now determine, so again see the question really is, should ask, find the number of such intermediate fields. Because this is an arbitrary extension, so the question of find all the intermediate fields doesn't really make sense. After doing this, we will do a specific example of such a thing where we can ask our finding the intermediate fields. So really the question is find the number of intermediate fields. So the number that we look for here is, so the number of such L is number of subgroups of order 4. So number of such L here is number of subgroups of order 2. So let's do this second case first, because this is more in some sense easy. So here subgroups of order 2 will be generated by an order 2 element. So this is really elements of order 2. Okay. So number of elements of order 2, each element will give a unique subgroup, right? Because if you have a order 2 subgroup generated by X and order 2 generated by Y, these are different means X equal to Y. So the only way they can differ is by that element. But what is the number of elements of order 2 in our group? That is exactly 7, because you have every non-identity is order 2. So there are 7. So this is easy. There are 7 such subgroups. But for order 4, you have to be a bit more, you have to do a bit more work. So let me do some more notation. So G can be thought of as, so Z is Z mod 2 cross Z mod 2 cross Z mod 2. So I'm going to, I don't want to spend too much time here, but let's start the process and I will let you work it out in detail for yourself. So let me write the elements like this: 0 0 0 1 0 0 0 1 0 1 1 0 1 0 1 0 0 1 0 1 1 and finally 1 1 1. Okay, so I'm going to call this 0, call this 0, call this x1, call this x2, call this x3. In some sense, they are the generators. Then this will become x1 plus x2, this will become x1 plus x3, this will become x2 plus x3, this becomes x1 plus x2 plus x3. So it's an abelian group. We are going to use additive notation. So we are going to use this. Okay, so here each xi and their sums has order 2. So the 7 subgroups of order 2 are going to be 0x1 is one, 0x2 is another, 0x3 is third one, and so on. But what are the subgroups of order 4? So order 2 are clear, there are 7 of them, but order 4, see, remember order 4, each of them has to be isomorphic to Z mod 2 cross Z mod 2, because there is no Z mod 4Z here, so they are all degree 2 elements, so they are all Klein 4 groups, but you have to be careful in writing these down. So I am going to clearly list them. First you can take 0, x1, x2, x1 plus x2. So basically you take any 2 and their sum will be a valid group. Similarly you take x1, x3, you get x1 plus x3. So for some reason I have sort of messed up the notation in my notes, but anyway let's do that here. I am not going to do full details anyway. So these are all distinct groups of order 4, right? But what else can we do? We can take 0 x1 and then we can take some other element, for example x1 plus x2. And then if you take their sum you get x2. So this is same as the first one, so I don't want this. So I'll take x1 plus x3. Then I get x3 again. So I don't want to take either of these elements. So maybe I'll take x1 let's see, I get x1 and x2 plus x3. That appears here, but that x1 is not here. So I get x1 plus x2 plus x3. Okay, there are 4 so far, and let me write it here. Then I'll take 0. I think if I take x1, I have already 1, 2, 3, and the remaining 2 elements will cover all the 6 remaining elements: x2, x1 plus x2, x3, x1 plus x3, x2 plus x3, and x1 plus x2 plus x3. So then I'll take x2, let's say. I've written x2 with x1 and x3, and I have x1 plus x2, x2 plus x3. So I can take x1 plus x3. So I do x1 plus x3, then I get x1 plus x2 plus x3. As you can see, this is different from any of the things that we have written. Okay, now I have 3 with x2, so that's already done. So I have 1, 2 with x3. So I'll take a third one with x3. With x3 I have covered x1 and x2, x1 plus x3, x2 plus x3. So let's take x1 plus x2. x1 plus x2 is not there, so I'll do x1 plus x2 plus x3. Okay, so I have 6 of them. So is there anything left? So I now can take one without x1 or x2 or x3. So then I can take x1 plus x2, x2 plus x3, and then if I add them I'll get x1 plus x3. So there are again 7 of them. Okay, so there are 7 such groups. So there are 7 such intermediate fields. So let me give some names to this. Let's call this L1, L2. I will use prime to denote the second case. L1, L2 to L7. I have L1 prime, L2 prime up to L7 prime. Okay, so these are all the intermediate fields. So let's agree now that there are exactly so two trivial ones, K and Q, 7 with in the first case, 7 with in the second case. So there are 16 intermediate fields. Okay, so let me also try to make an attempt. I will make an attempt to draw the tower of fields. So you have K and you have Q here, but the L1s will appear, L1 primes will appear. So let me just use my notation here. So actually I called this prime and this not prime. Okay, so the without prime are degree 2 over under Q, so these will appear with degree 2. So L1 prime, L2 prime, L3 prime, L4 prime, L5 prime, L6 prime, L7 prime. Okay, so before I write this, it's clear that there are no more. And these are all different, 16 different. First of all, these are all different because their degrees are different. And the corresponding, so K is of course not equal to any of the Li primes or Lis. And similarly, Q is not equal to any of these. And any Li prime is not equal to any Lj for degree reasons. And now among Lis, they are all distinct because the corresponding groups are distinct. Similarly, among the Li primes, there are no common ones. So there are no more, and these 16 are all distinct. All distinct is because of what I just said, and there are no more because if you put any in between K and Q, it's either Q, we are done in that case, K, we are done in that case. Otherwise, K colon L will be 4 or 2. If it's 4, it appears in case 1. If it is 2, it appears in case 2. So that means it must be one of these 16. So there are exactly 16 intermediate fields. So to speak, we are really solved this problem, right? Find the number of intermediate fields. But I wanted to give an idea of how the inclusions among these works. So these are all 2. But now, so L1 prime, let's say, is the fixed field of the first order 2 group we take. Let's say 0, x1. So this is L1 prime. So I don't know what I am doing, but this is not prime, right? This is without prime. So these are degree 2. So just it depends on the notation that we are using, but let's say this is the fixed field of this. Then L1 prime, and let's say L1 prime is the fixed field of this. So this is H1 prime, and this will be K, the fixed field of x1, x2, x1 plus x2. Okay, so this will be contained in L1, and now depends on what L2 and L3 are, but let's say L2 is fixed field of, so I am going to squeeze this here, 0 x2, okay, and this is the fixed field of 0 x3. So there will be an inclusion here and it will be degree 2, but there is nothing here, right? This can't exist. There is no line here, right? Because 0x3 is not contained in this. This is the application of the main theorem. Only way that you will have an inclusion is that there is a reverse inclusion of the groups. 0x1 is contained in this, so L1 prime is contained in this. 0x2 is contained in this, so this will be contained in this. So there is nothing here. But what will this be? there will be one more that contains this, and that would be 0 x1, maybe this is k power 0 x1 plus x2, whatever that is, there will be an inclusion here. Okay, and L1 prime will not be contained in any other things. So basically we can, and of course underlying all of these is Q. So these are all 2, of course. Okay, so now the missing thing in this picture is what lines to put between primes and LIs and LI primes, which I mean this depends on how you are calling these things, and you can prove that each LI is contained in exactly one, or each Li prime is contained in exactly 3 Lis, Ljs. Okay, so each Li prime, for example L1 prime is contained in L1, L2, L4 in my notation here. Okay, so I cannot erase this, but it should be L4. So Ljs, so L1 prime is contained in L1, L2, L4, maybe L2 prime is contained in something else, so it depends on the notation, but that is the picture of this. Now let me end this class with a specific example of such a thing. So let us take K to be Q adjoint square root 2, square root 3, square root 5. Okay, so the first thing to check is K over Q is an extension satisfying the hypothesis of the problem. Okay, so and this is because, so first you note that, so this I would like to do this in detail because this kind of thing is important. So let me carefully check some of these things. So first you have okay, so it's been already quite a bit of time I spent, so maybe I'll just stop this class now so that you can start fresh with this specific example again. So let me stop this class now. In the next video we will work out this specific example in detail. Thank you.